right. Okay, so we were talking last time about two different constructions that you can make out of a collection of vectors, right? So we have vectors v1 up to vn in Rd, and then you can do two things with them. You can construct the zonotope, which is the Minkowski sum of the vectors. And we can construct the hyperplane arrangement consisting of the hyperplane vi dot x equals 0 for each I. And so we've done some examples of this. And for example, if you have here's v1, here's v2, and here's v3, then the zonotope looks like this. And the hyperplane arrangement looks like this. Where the normals are precisely these vectors, right? So here's v1, v2, and v3. Okay. And then I define two fans. So first we define the faces. The faces of the arrangement. They form a fan. And then the other fan that we formed was by doing the following thing. For each F face of the zonotope, we defined n sub f to be the directions such that the function c is maximized at the face f. Right? So we did this picture where we said, for example, if we look at this face, this vertex, then that vertex is maximal for all of these directions. Maybe let me just overlay these pictures. I think it'll be a little bit easier to see them then. So this is n sub f. And then we consider the fan. The normal fan consists of all of these cones for all the different faces, right? Okay. And the statement that I made at the end of last time that I want to prove now is that these two constructions give you exactly the same fan. Okay. Question? So it depends where. Oh yeah, so the zonotope is in R to the D, and that means that this is in the dual. Yeah. Which is why I hesitated to overlay the pictures, but just for your visual pleasure, you have to draw it like this. I don't know how people cannot draw it like that. That's really how I see it. But yeah, just think that black is R to the D and blue is R to the D dual. Okay, and so then we have this proposition that the normal fan of the zonotope is the fan of the arrangement. In other words, that these two pictures match. Okay. Okay. So let's prove this. We have something like Z is a sum of V1 plus dot 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 plus Vn. Okay. Let's say that these all come with directions, and then I'm going to introduce a notation. Let's call the head of V1 plus and the tail V1 minus. Okay. And this is Vn plus, and this is Vn minus. Okay. And now let's do the following thing. How do I get a handle on this normal fan? What I'm going to do is I'm going to take a point in the dual space. So let's consider C in RD dual. Okay, so some blue direction in this picture. Okay, and then in order to know what phase of the normal fan C is in, what I have to figure out is what is the maximal phase in that direction. Okay, for example, if I pick C in here, then the maximal phase is going to be F. So how do I determine the maximum phase, which we have denoted Z sub C? Well, one thing that you should remember is that if you want to compute the maximum phase in some direction of a Minkowski sum, then you can do it summand by summand. Okay, so we can say what is V1 sub C plus dot 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 plus what is Vn sub C. Okay. So we proved this lemma about Minkowski sums, and the point is that for a segment, this is actually kind of easy to do. Okay. Because what can V1 sub C be? What can the maximal phase of V1 be according to this linear function? Well, there's not a lot of possibilities. It's either V1 minus, V1 plus, or the whole thing. And it's V1 plus if the vector points positively with respect to V1. It's V1 minus if it points negatively. And it's all of V1 if it's orthogonal to it. So this is going to be equal to V1 plus if V1 dot C is bigger than 0. It's going to be V1 minus if v1.c is less than 0. And it's going to be the whole segment v1 if v1.c is equal to 0. Okay? So that's the first one. But I'm supposed to do it for each one, right? So then, I do the same thing for v2 and so on, up to for vn. Okay? But then the point is that if you want to know what this maximal phase is, then it's like you have to answer this questionnaire, right? What is v1.c? Is it bigger, less than, or equal to 0? And what about v2.c, and what about vn.c? And if you answer that questionnaire, then you will know exactly what the maximal phase is. Okay? So that maximal phase, C sub c, is determined uniquely by filling in. We're going to do it like in elementary school. So remember, they will give you a little thing like this. Then you have to write in either a greater, a less than, or an equal. Okay? So less than, greater than, or equal. Okay? And so on. So to know the maximal phase, you have to basically decide all of these things. But if you see what I'm doing here is exactly, I'm describing a phase of the arrangement, right? Because when I ask this question, really what I'm asking is, another way of saying it is, what side of the hyperplane v1.c equals 0 am I on? Am I on the positive side of that hyperplane? Am I on the negative side, or am I on the hyperplane? So another way of saying it is, in other words, what side of the hyperplane hi is C on for I between 1 and n? Okay? But as we discussed last time, saying what side of each hyperplane you're on is exactly describing a phase for you. Okay? In other words, what phase of the arrangement is C in? Okay? And so the point is that C has a certain maximal phase if and only if C is in a certain phase of the arrangement. Okay? And so that means that there's a one-to-one correspondence between the cones of the normal fan of the zonotope and the cones or the faces of the arrangement. Okay? And that's the proof. Okay? You guys have any questions about that proof? I think I want to say this. I'm basically going to say this again, but in a different way, in a picture. So let's do it here. Let's take each one of these hyperplanes, and they're numbered, right? So this is 1, this is 2, and this is 3. Okay? And then what I would like to do is, so I'm going to introduce something called sign vectors. What I want to do is I'm going to say the following. I'm going to say each hyperplane has a positive side and a negative side. And that's determined by which way the arrow is pointing, okay? So for example, let's look at this region right here, okay? So this region is on the positive side of 1. So I'm going to put a plus to say that. Then it's on the negative side of 2. So I'm going to put a minus to say that. And then it's on the negative side of 3. So I'm going to put a minus sign there. Okay? So let's do it for this one, for example. This one is on the positive side of 1, positive side of 2, and positive side of 3. Okay? Do you guys see how I'm getting these signs? Now you'll see, for example, that if you have a plus, minus, minus in this region, and if you cross hyperplane 2, then you just have to flip the second coordinate, right? So that's plus, plus, minus. Okay? Between here and here, I flip coordinate 3. Between here and here, I flip coordinate 1, so I get minus, plus, plus. Between here and here, I flip the second one, so minus, minus, plus. And between here and here, I flip the third one, so minus, minus, minus. Okay? So those are going to be the sign vectors of those faces. But I also want to do it for the smaller dimensional faces. Okay? So for example, what should I call this phase right here, this one? When you notice precisely what I want to do is not have to point. I want to give it a name. So what would you call it if I force you to name it? 0 plus plus. Because you're on the first hyperplane and then positive side of the second one, positive side of the third one. Okay? And I keep doing that. So this is plus plus 0. This is plus 0 minus. This one is 0 minus minus. This one is minus minus 0. And this one is minus 0 plus. Okay? And I should also give I'm missing one phase that I haven't labeled, which is this one, right? This one. That one also deserves a name. I am on hyperplane 1, on hyperplane 2, and on hyperplane 3. So that's the 0, 0, 0 phase. Okay. So that's a very natural way of labeling the phases. Okay? Now, the point is that that labeling translates directly to a labeling of the faces here. Okay? For example, what would you call the face F? Which is just a vertex. Well, you would go here and see what the corresponding region is called, and it's called plus minus minus. Okay? So this is called plus minus minus. Now, why should I call that plus minus minus? Well, the reason is that plus minus minus, that vertex is the Minkowski sum. So we call this F, right? F is the Minkowski sum of, in V1, choosing the plus in V2, we choose the minus, and in V3, we choose the minus. Okay. And if you do the Minkowski sum of the plus face of V1, the minus face of V2, and the minus face of V3, and if you do it carefully, you're going to see that that's exactly where you're pointing. Okay. Let's do it for a different one. For example, for this one. So what should we call this phase? Well, according to that picture, we should call it plus plus 0. So what am I saying in terms of the Minkowski sum? I'm saying that G is the Minkowski sum of, in V1, I take the plus, the head of V1. In V2, I take the plus. Okay? And in V3, I get both the plus and the minus. I get the whole segment. And so when you do the Minkowski sum of this point, and this segment, you're going to get a segment that is shoved over that direction and this direction, so you're going to get exactly G. Okay. And so this is a concrete way to understand this correspondence. Okay. Do you guys have any questions about it? Yep.
Is it easy to see that the normal fan of any zonotope is pointed fan?
Well, I would argue that I just proved it because what should I call? Okay, so we're doing it kind of by dimension. So here points are black, segments are blue. So then what's red? Red is the whole thing. And so the point is that the point of the fan corresponds precisely to is the dual to the whole polytope. Okay. This face is called 0, 0, 0. And again, the reason why it's 0 is that if you're plus, you choose the head. If you're minus, you choose the tail. And if you're 0, you choose the whole segment. So if you do 0, 0, 0, you're doing segment plus segment plus segment, so you get the whole polytope. The other thing that you should notice is that there is this correspondence flips the dimension, right? So vertices here become two-dimensional things here. Segments become segments, and two-dimensional things become points. Okay?
I understand that correspondence, and that makes good sense. But we're trying to say that the normal fan of this is isomorphic to the fan of the hyperplane.
Uh-huh.
So I believe the one-to-one correspondence, so therefore I believe that cone must be pointed. So I was wondering, is there an easy way to see that the normal fan is actually a pointed fan over here? Because I don't see that.
I see. So you believe the proof, but you don't see why it's true. That.
Well, I see.
I mean but it's fair. I mean, sometimes you can prove something and not understand it. I think that happens very often. So we proved it and you believe it, but how can we understand that it's pointed? I guess I would say because if you choose C to be 0, 0, 0, then what is the maximal phase according to C? Well, 0, 0, 0 dot product with anything is 0, and so that means that the whole polytope is maximized by that. So that's my best intuition for why 0, 0 is like it is, because if 0, 0, 0 corresponds to the full polytope, then any positive vectors are going to correspond to smaller parts of the polytope. That's the best intuition that I can give you. Okay. Now, there's something that I'd like to point out to you, which, just by looking at your faces, I know you agree with me. I know you followed this more easily than you followed this. And that's one of the points that I wanted to make when I said that I think arrangements are easier than zonotopes. If you try to deal with the faces of the zonotopes, we can do it, but it's a little bit muddy. I mean, you can understand it, but I think this is easier to understand. You're just saying, for each hyperplane, what side are you on? And you don't have to worry about Minkowski sums and what point was where. And I think it's easier, okay? And that's one point of this theorem that sometimes it's very often, if you want to know something about the zonotope, it's easier to translate it to the arrangement. So let me summarize this by saying and I'm just going to write in words what I just drew in pictures. This list of signs are called the sign covectors of V. Okay. Kind of a fancy name, but it's just that collection of signs. And so the point is that we have bijections between the signed covectors of V the faces of the arrangement and the faces of the zonotope. Now, one thing that you have to notice actually is that there is a face that we're missing. The empty face here, because remember that okay, so imagine that I didn't erase the zonotope. I'm pointing to a zonotope here, and every polytope has an empty face, the empty face. What should that correspond to here? It doesn't really. You might want to make it correspond to the entire picture, but that's not a face. Right? You agree that the entire thing is not a face of the arrangement because I define a face to be specifying what side of each hyperplane you're on. So you don't get to be on all the sides of all the hyperplanes. Okay? So that bijection works perfectly, except that it just loses that empty face. Okay? It's no big deal. You didn't like that empty face to begin with, so we lost it, and maybe you're happier now. Non-empty faces of the zonotope. Okay. So the empty face gets lost in this bijection. And let's say this precisely, that if here we tack on the adjective k-dimensional, then here we're going to get d minus k-dimensional. Okay, so this bijection swaps the dimensions. Okay. So basically then, what I'm going to do for the rest of the semester is talk more about the arrangement, which is a little bit easier. Okay? And you should keep in mind that for a lot of the theorems that we prove about the arrangement, you can translate it into something about the zonotope. And occasionally I'll say that to remind you. So when we prove things, remember that they have to do with the zonotope also. But I think a lot of things are going to be more apparent here. Okay? So let's keep this here in a corner so that you have it present in the back of your head. And we're going to move on to the last topic of the class, which is hyperplane arrangements. And I should tell you that for most of the rest of the course, I'm going to be following Stanley's lecture notes on hyperplane arrangements. It's called Introduction to Hyperplane Arrangements. And this thing is actually a PDF. It's online, and it's linked from the course website, so you can find it there. Okay. So a hyperplane arrangement is a collection of hyperplanes. And I already said this last time. Except that, so a collection of hyperplanes in R to the D, where the ith hyperplane is the axis in R to the D such that AI dot X equals BI. Okay. And so you'll notice that I changed my mind from last time, because last time I had everything equal to 0. And this time I have it equal to BI. So I told you last time that most of the rest of the class, we were going to assume that hyperplanes are going through the origin, but actually I don't want to assume that. So for us, a hyperplane arrangement is just going to be anything like this, you might call it affine, because these are really affine hyperplanes. Okay? And if everything happens to go through the origin, I'm going to call it central. So central if all BIs are 0. Okay? So faces, what are faces? Well, I already defined what they are, as I already defined. Okay. For each hyperplane, you specify what side of the hyperplane you're on, or you are on the hyperplane. And let me define regions to be the full dimensional faces, okay, the d-dimensional faces. So that means that you don't get to be on any other hyperplanes. You have to make up your mind. For each hyperplane, you're really either on the positive side or on the negative side. D-dimensional faces. Okay. Now, one thing you'll notice is the following. Maybe this is easier to see if I have a picture. So there's a hyperplane arrangement in R2, right? In R2, hyperplanes are lines. And so the regions are all of these, right? Region, 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 and so on. And one thing you should notice is the following. If I take the space where I live in, and I delete the arrangement, if I just throw out all the hyperplanes, then the red pieces are exactly the connected components of what remains. The connected pieces. So connected components of R to the D minus the hyperplanes. Okay. When I say connected pieces, I mean that you can walk from between any 2 points of that piece. Okay, so for example, the point is that you cannot walk from this region to this region without falling into a hyperplane. So if you throw the hyperplanes, then you cannot really cross them anymore. So that disconnects the space. Okay. So those are the regions. So let's say that R of A is the number of regions of A, and B of A is the number of bounded regions of A. I'm going to put a bit of an annoying adjective here, relatively bounded. Okay? And this should remind you of the relative interior of a polygon. It's kind of the same thing. Okay? So for example, what is R of A here? Well, you just count how many regions there are. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Okay? And of those, there's exactly 3 bounded ones. Okay? Now, let me explain to you maybe a little bit loosely. What is this relatively about? If you look at this arrangement, it has one bounded region. Okay, that's indisputable. But now, what I want to consider is this arrangement where you kind of take this and you expand it a dimension. Okay, so it's going to look kind of like this. Can you kind of see that? So So then the arrangement that I had earlier was a slice of this one, right? If you slice this arrangement with a plane, then you get the one that I had drawn earlier. Now the thing is that this arrangement doesn't really have any bounded regions because everything has this extra direction that you could walk onto indefinitely. But I want to count this as a relatively bounded region. Okay, and so the point is that if all my hyperplanes contain the same parallel direction, then I want to mod out by that direction. Okay, so instead of considering it like this, because all of the hyperplanes contain this direction, then I just want to think of this as really being this arrangement. And this is where I want to count bounded things. So if this arrangement is A, then this is called the essentialization of A. Okay.
Is that the same thing as a n-dimensional polytope being better than n+1 dimension?
Yeah. I'm trying to think of what the... I'll show you an example in just a second. But yes, the answer is yes. Actually, that's exactly the next thing that I want to do. I want to show you, so this is one example. It's an easy two-dimensional example. But as you know, in this class, we don't like to stop in 2 dimensions, and we want to consider n-dimensional examples. And this is my favorite hyperplane arrangement. It's called the braid arrangement. It's a pretty simple arrangement. We call it an-1, and it consists of the hyperplanes xi equals xj for 1 less than or equal to I less than or equal to j less than or equal to n. Okay. So for example, if n is equal to 3, then we have the arrangement A2, which consists of the hyperplanes x1 equals x2, x1 equals x3, and x2 equals x3. Right? Now, what does this arrangement look like? Well, it's 3 planes in 3-dimensional space, so we should be able to draw this. Now, how do these intersect? They all intersect not only at 0. So Rika's showing me what happens. What happens is that they intersect on a line, on a common line. Because you see, if you intersect these 2 equations, you're saying x1 is equal to 2 and x1 equals x3. So that means that all 3 variables are equal, and then this is automatically contained. It automatically contains that intersection. So the intersection of these 3 hyperplanes is the line x1 equals x2 equals x3, which is a 1-dimensional space, right? So this looks like this. It's kind of like that picture, but a little bit simpler. It looks like this. Okay. Where this right here, they all go through this line, which is the line x1 equals x2 equals x3. Okay. Okay, so that's my example, but then this is an example of an arrangement that is not essential, and I would like to essentialize it. And the way that I essentialize it is that I just kind of drop this extra dimension and just make it look like this. Okay. Just going to take a slice like this. Now let's see what are the normal directions of this. Well, it's going to be something like this: E1 minus E2. This is actually possible to do incorrectly, so I have to be careful. E1 minus E2. E2 minus E3. E1 minus E3. So you see that this is the plane x1 equals x2, x1 equals x3, and x2 equals x3. Let's write the equations here. x1 equals x2, x1 equals x3, and x2 equals x3. Okay? So what are the regions here? So to describe a region, I have to say, for each hyperplane, what side am I on? So I have to decide for each I and j, is xi less than or bigger than xj? Okay? But I have to do this for every single pair. And so that means that if I want to, once you decide for each pair I and j which variable is bigger than which, when you're done with all those decisions, you will have specified a linear order of the variables, right? If you know who's bigger than who, if you can compare every pair, that means that you know how to order them left to right. Okay? So, and again, maybe let's do it in this example. So, for example, here, x1 is bigger than x2. And according to this, x1 is less than x3. Right? Because the dot product with E1 and E3 minus E3 is negative. So that means that so I had said x1 is bigger than x2, and according to this, x1 has to be less than x3. Okay, and according to this, x3 has to be bigger than x2. Okay, so you get to be in this region if x1 is bigger than x2, x3 is bigger than x2, and x3 is bigger than x1. In other words, you get to be in this region if this is the relative order of your coordinates. Okay. So what you're doing is, so you have to, so you decide the relative order of x1 up to xn. Okay. Let's see it. Actually, let me do this with another color so that it's. So let me denote this 3, 1, 2, because x3 is bigger than x1 is bigger than x2. Okay. So what happens when you cross this hyperplane? You're crossing the hyperplane x1 equals x2. So that means that now, instead of x1 being bigger than x2, they're going to switch. And x2 is going to become bigger than x1. So this is going to be where x3 is bigger than x2 is bigger than x1. So the order is 3, 2, 1. Okay. Now what happens when you cross this hyperplane? Then 2 and 3 switch their order. So this becomes 2, 3, 1. Okay. Now what happens when you switch here 1 and 3, then you get 2, 1, 3. Then here you switch 1 and 2, and you get 1, 2, 3. And here you switch 2 and 3, and you get 1, 3, 2. And here you switch 1 and 3, and you get 3, 1, 2. And you should appreciate that I did this very carefully so that it all matched up. Because, for example, you notice that here I didn't have to ever swap 3 and 2. Right? If I walk out of this hyperplane, I switch 1 and 2. If I walk out of this hyperplane, I have to switch 1 and 3. And they're neighbors. And you can switch neighbors, and that works out well. But if you had to switch 2 and 3, then you would be in trouble. But this is saying, if you want to switch 2 and 3, you better switch both this and this. You can't just do it in one swoop. It takes you 2 steps. Okay. So then you see what do the regions correspond to? Permutations, right? They're permutations. So the regions of an minus 1. So you see why this is my favorite arrangement. Permutations of Sn. And so that means that the number of regions is precisely n factorial. Okay? Oh, hold on. I'm getting red here. Okay, hopefully we didn't lose sound right there. So I hope this looks familiar to you, especially if I tell you, okay, so what's the dual picture here? It's my favorite polytope, the Federico, right? And so the dual thing is, and let's draw them maybe in orange, since that's the color that I gave to these things. It looks like this. And these are naturally the names that we give to these vertices. And if you think about it, actually, this shouldn't really be a big surprise, because this is the arrangement of these equations. So what are the vectors? The vectors are E1 minus E2, E1 minus E3, and E2 minus E3. And so what's the dual zonotope? It's the Minkowski sum of these things, E1 minus E2 plus E1 minus E3 plus E2 minus E3. And we proved that that's the permutahedron because these are the different pairs of EI and EJ. So this is the permutahedron, which we call pi 2. Did we call it pi 2 or pi 3? It was pi n minus 1, I think.
That makes sense.
Yeah, that's why I call this an minus 1. We call this pi 2 because it's 2-dimensional, even though it looks like it lives in 3 dimensions, but it's 2-dimensional. And this answers your question, Jimmy, because the point is that this is 2-dimensional, but it really lives in 3 dimensions. Okay. But it's a 2-dimensional thing. It's a terrible picture, but but I hope you understand. So it's a 2-dimensional picture that lives in 3 dimensions, and it's kind of the dual notion that you have a hyperplane arrangement that has an extra dimension. And so you mod out by that. So modding out by a dimension here is the same thing as just taking the correct slice in this picture. Okay. Okay. So let me give you an exercise, and it's an exercise that I would really, really like you to do, which is do that homework problem about the permutahedron now. Do the homework problem of the permutahedron. So the homework problem asks you to describe the faces of the permutahedron. But you see now you have great tools, because now we're saying the faces of the zonotope correspond to the faces of the arrangement. And you had a lot of trouble describing the faces of the zonotope. So what I'm asking you to do is describe the faces of the arrangement and explain why the faces of the arrangement correspond to ordered set partitions. And then you'll see that that's a lot easier having this extra tool. That's a great idea. Let me think about it. That might be, I was actually going to think about it now, what homework I should give you, and that might be the homework. No, let's do that, actually. That's a lovely homework. So your homework problem is to do that homework problem again about the faces of the permutahedron. This is a very good homework for you. Okay. It's a lot easier, by the way. That's the point.
One question. So with these hyperplane arrangements, this braid arrangement generate a group SN. Would that end up being the implications of this? So we can think of the hyperplanes as reflections.
So Tito has this beautiful question. If you guys want to think about this, there's actually a group lying around here. So remember, SN is a group, and you're kind of seeing it in action where. What we're doing here is the transposition of 2 and 3. This is the transposition of 1 and 2. And you can see the group structure of the permutation group as just bouncing around in this picture. And if you want to know more about this, I taught a whole semester on it. This is the theory of Coxeter groups. So, what are they called? Coxeter groups. And actually, the first lecture of that class, I explained exactly this picture. So if you're curious, you can look at it there.